We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello everyone, my name is HIRENKUMAR, working as Assistant Professor in Mahatma Gandhi Institute of Technical Education and Research Center NAVSARI in Mechanical Engineering Department. In my previous video, we have seen the 2 examples of reverse Carnot cycle and Bell-Coleman cycle. Now in this video, we will see another 2 examples of Bell-Coleman cycle. So here is the example. The refrigerating machine of 6 ton capacity working on Bell-Coleman cycle has an upper limit of pressure of 5.2 bar. The pressure and temperature at the start of compression are 1 bar and 16 degrees Celsius respectively. The compressed air is cooled at constant pressure to a temperature of 41 degrees Celsius, enters the expansion cylinder, assuming both expansion and compression process to be isentropically with gamma is equal to 1.4. So calculate coefficient of performance, quantity of air that is circulated per minute, piston displacement of compressor and expander, bore of compressor and expansion cylinders. The unit runs at 240 rpm and is double acting. Stroke length is given, that is 200 mm, and power required to drive the unit that need to find out, gamma and Cp is given. So first we need to draw the cycle. So Bell-Coleman cycle, if we go for the PV and TS diagram, then this is PV diagram and TS diagram. So 1, 2, 3, 4. One, two, three, 4. So here now we need to find out the data. So what are the data given? That is capacity of machine, that is Q. So Q is given, that is 6 tons. Then another thing, that is the upper limit of the pressure, that is 5.2 bar. So what is the upper limit? That is P2 P3 here, that is P2 equal to P3, that is equal to 5.2 bar. Then the temperature and pressure and temperature at the compression are 1 bar and 16 degrees Celsius. So here the pressure P1 is equal to P4, that is equal to 1 bar, and temperature at the starting of the compression, that is T1, and that is equal to 16 degree Celsius. Also the compressed air is cooled at a constant pressure to the temperature of 41 degrees Celsius, and after compression it is cooled up to T3, that is 41 degree Celsius. So these are the data are given. So Q, then P1 equal to P4, that is equal to 1 bar, P2 is equal to P3, and that is equal to 5.2 bar, T1 that is equal to 16 degrees Celsius, and as I said how to convert in Kelvin, and that is equal to 289 Kelvin. T3, that is equal to 41 degrees Celsius plus 273, that is equal to 314 Kelvin. Also gamma is given 1.4 and Cp is given 1.003 kilojoule per kg Kelvin. So these are the data given. So now we are starting the solution. So first, what we have to do, there are two cycle, compression and expansion, and both are isentropic, and for isentropic process T2 by T1 is equal to P2 by P1 whole raised to gamma minus 1 upon gamma. So that is equal to 5.2 by 1 raised to 1.4 minus 1 divided by 1.4, that is equal to 5.2 raised to 0.286, and that is equal to 1.6. So from that we can find out T2, and that is 1.6 into T1, and that is equal to 1.6 into 289, so 462.4 Kelvin. Same as T3 by T4, that is equal to P3 by P4 whole raised to gamma minus 1 upon gamma, and that is equal to same 5.2 divided by 1 whole raised to 1.4 minus 1 divided by 1.4, so that is equal to 1.6. So from that we can find out T4, and that is equal to T3 divided by 1.6, so 314 Kelvin divided by 1.6, and that is equal to 196.25 Kelvin. So here we are having two remaining temperature, that is T2 and T4. So from this we can find out the COP, and that is equal to T4 divided by T3 minus T4, so 196.25 divided by 314 minus 196.25, that is equal to 1.674. so that is our first answer. So COP of the system. So that is first what we need to find out. Second one is quantity of air in circulation per minute. So for that, mass of air that need to be find out. So MA, that is mass of air. Now we know that mass of air, but for that we need to first find out the heat that need to be extracted from the machine. So whatever the heat need to be extracted from the machine is QA. If we say Q, that is heat absorbed, that is Cp delta T, and that is Cp T1 minus T4, or we can say the amount of heat that need to be removed per kg of air. So that is equal to 1.003 into 289 minus 196.25, and that is equal to 93 kilojoule per kg. So this is what the amount of heat that need to be required per kg of mass of air. Now total capacity. So our refrigerator has total capacity of 6 TR, that is Q. So 6 into 210, that is equal to 1260 kilojoule per minute. Now if we divide this capacity Q with QA, then we will get the MA. So 1260 divided by 93, so that is equal to 13.548 kg per minute. So this is our second answer. So this is the mass that need to be circulated through the system per minute. Now piston displacement. So now we know that RA, that is the gas constant, characteristics constant, that is equal to Cp gamma minus 1 upon gamma, and that is, if we find out, then that is equal to 0.287 kilojoule per kg Kelvin, or we can say 287 joule per kg Kelvin. So now P1 V1 is equal to MA RA T1. Now if we need to find out V1, then MA RA T1 divided by P1. So all data we are having. So if we calculate by putting T value, then 13.548 into 287 into T1, that is 289 Kelvin, divided by P1, that is 1 into 10 raised to 5 Newton per meter square, and from that volume can be find out 11.237 meter cube per minute. So now if we take ratio V4 by T4 is equal to V1 upon T1, then we can find out V4, and that is equal to V1 into T4 by T1. So 11.237 into 196.25, that is T4, divided by 289, and V4 we will get, that is 7.63 meter cube per minute. So here are the third answer, and that is we need to find out piston displacement of compressor and expander. So that is V1 and V4. Now next that we need to find out is bore of compressor and expansion cylinder. So for that we are having N, that is given 240 rpm, L, that is given 200 mm, or we can say 0.2 meter. Here in the problem it is already given, that is 240 rpm and 200 mm. So V1 is equal to pi by 4 into T square into L into 2 into N, because having double stroke. So if we put the value of V1, that is 11.237, and if we put all the values, then we can find out the L value, that is 0.2 into 2, and for double stroke so we are having 75.4 D square equal to, so therefore D can be find out is 0.386 meter or 386 mm. That is for compressor bore. And for the expander for bore, same as V4 pi by 4 D square into 2 into 2 into N, because it is double stroke. So from this, by putting the value, we can find out 7.63 is equal to pi by 4 t square into 2 into 2 into 240. So D will be our 0.318 meter, so that is equal to 318 mm. So this is our fourth answer, that is the bore of the compressor and expander. Now the power, the power that can be find out by the work done, and for work done the amount of heat need to be absorbed, that is by the air. So that is equal to MA Cp T1 minus T4. So 13.548 1.003 into 289 minus 196.25, and that is equal to 1260 kilojoule per minute. Or if you can also take directly from here, that is we have found capacity, total capacity, that can be taken directly over here. So work done per minute can be find out by the Q absorbed divided by COP, and that is 1260 divided by 1.674, so 752.7 kilojoule per minute, and power P will be equal to work done divided by 60, so 752.7 divided by 60, and that is equal to 12.54 kilojoule per second, or we can say 12.54 kilowatt. So that is our last answer. So this is how the whole example can be calculated. So our next example is also for the Bell-Coleman cycle. So in an open cycle air refrigeration machine, air is drawn from cold chamber at -2 degrees Celsius and 1 bar and compressed to 11 bar. So -2 degrees Celsius, 1 bar and 11 bar. So these are the limitation of pressure. Then it is cooled to the pressure to this pressure to the cooler temperature of 20 degree Celsius. So T1 and T3 is given, and then expanded in expansion cylinder and returned to the cold room. The compression and expansion are isentropic, so it is directly given, that is isentropic, and it follows PV raised to gamma equal to constant. So they also ask to draw PV and TS diagram of the cycle, and capacity is given 15 tons. So we need to find out COP, rate of circulation of the air in kg per minute, piston displacement, and power. So as we have seen in previous example, we are having PV diagram, and TS diagram, so here two isentropic processes are there and two isobaric processes are there, and it follows PV raised to gamma equal to constant. So if we list out the data, then what we have given, T1 is equal to -2 degrees Celsius, that is equal to 271 Kelvin. T3, that is equal to 20 degrees Celsius and equal to 293 Kelvin. P1 is equal to P4, that is equal to 1 bar, P2 is equal to P3, and that is equal to 11 bar, gamma that is equal to 1.4, and Q that is equal to 15 TR. So as we have calculate T2 and T4 in previous example, same ways we can find out here also. T2 by T1 is equal to P2 by P1 whole raised to gamma minus 1 upon gamma, so that is equal to 11 by 1 whole raised to 1.4 minus 1 divided by 1.4, and that is equal to 1985. Same for T3 by T4. So here T2 is equal to 1.985 into T1, and that is equal to 538 Kelvin. Same as here T4 will be T3 divided by 1.985, and that is equal to 147.6 Kelvin. So from that we can find out the COP of the system, that is T1 minus T4 divided by T2 minus T3 minus T1 minus T4, that is theoretical COP. So if by putting the values we are getting 1.015, that is our first answer. Then rate of circulation of air, and for that we need to find out first amount of heat extraction per minute, and that is 15 into 210, that is equal to 3150 kilojoule per minute. So QA will be CP T1 minus T4, that will be 123.4 kilojoule per kg. So MA will be 3150 divided by 123.4, so it will be 25.5 kg per minute. So this is our second answer. So this example is also same as the previous one. So here also P1 V1 is equal to MAR RAT1, and from that we can get V1 is equal to MA RAT1 divided by P1. So we can find out by putting the value, that is equal to 19.8 meter cube per minute, and same ways V4 can be find out 10.8 meter cube per, sorry, that's just a meter cube. So this way we can find out V1 and V2. So these are the volume that we meter cube per minute for piston displacement, for compressor and expander. And same ways we can also find out the net work done, W, that is equal to MA CP T2 minus T3 minus T1 minus T4. Here we can't take directly from the capacity, so MA, that is 25.5 into 1, and putting the value 538 minus 293 minus 271, 147.6. So we are having 3100 kilojoule per minute, and from that power will be 3100 divided by 60, and that is equal to 51.67 kilowatt. So this is the theoretical power for the refrigeration machine, and theoretical power per kg of or per ton of refrigeration is 3.44 kilowatt per TR. So this is our final answer. So these ways we can find out the COP and power for the Bell-Coleman cycle. So these are the examples for reverse Carnot cycle and Bell-Coleman cycle. You can also solve the example in various types of example by using the equations. Thank you for watching.